Take a glass beaker filled with solid ice cubes and set it over a steady, burning heat source. The logical expectation here is straightforward. As long as that burner remains on and heat is flowing into the beaker, a thermometer resting inside the glass should show a continuous, unbroken rise in temperature. But look at this temperature time graph of the experiment. The temperature rises predictably until it hits exactly 0 degrees Celsius. Then it completely flatlines. The burner is still roaring, pumping thermal energy into the glass, but the temperature refuses to budge. Eventually, the line starts moving upward again, climbing steadily until it hits 100 degrees Celsius. At that point, the exact same thing happens, a second, even longer thermal plateau. During these specific thermal plateaus, adding energy to a substance does not make it hotter. The heat is going somewhere, but it's completely vanishing from the thermometer. If the thermometer isn't capturing it, where is that constant stream of thermal energy actually going? Inside the glass, the applied energy is doing heavy mechanical work. It causes the solid ice molecules to vibrate aggressively, pushing them harder and harder until their rigid atomic bonds physically snap apart. Physicists call this a phase change, specifically melting or vaporization. The heat is entirely consumed by the effort of tearing down the old molecular structure, leaving zero leftover energy to raise the actual temperature. During these plateaus, the substance enters perfect thermal equilibrium. That means the solid ice and the liquid water are peacefully coexisting in the exact same space at the exact same temperature. These specific temperatures mark the physical boundaries where incoming energy shifts from heating a substance to dismantling its molecular structure. Temperature appears to hold complete authority over these boundaries. There is a second invisible environmental force that can overrule it entirely. That hidden variable is pressure, and if we manipulate it, we can actually force a phase change without adding a single drop of heat. To see this in action, imagine a solid block of ice. We drape a thin metal wire over the top of the block and hang a heavy 5-kilogram weight from each end. The wire concentrates all 10 kilograms of force into an incredibly narrow line. This extreme, localized pressure physically crushes the ice lattice, forcing it to melt into liquid water directly beneath the wire, even though the room is freezing. As the liquid water forms, the wire sinks deeper into the block. But the moment the wire passes through, the pressure above it returns to normal, and the water instantly refreezes into solid ice. This phenomenon, called regelation, is the exact reason ice skating works. The immense pressure of the skater's blade melts a microscopic layer of ice, creating a slick runway of lubricating water that vanishes the moment the skate glides past. Increasing the environmental pressure mechanically forces the molecules closer together, making it easier for that rigid crystal structure to collapse into a fluid. If crushing ice with pressure forces it to melt, can manipulating pressure force hot water to boil in a cold room? We can test this. We boil some water in a round-bottom glass flask, remove it entirely from the heat source, and hammer a cork tightly into the opening to seal it. We leave the sealed flask on the table to cool down to about 80 degrees Celsius. The surface becomes completely still. All boiling action has stopped. Now we do something completely counterintuitive. We take that sealed glass flask, flip it upside down, and pour a steady stream of ice-cold water directly over the outside of the glass. The water inside the sealed flask immediately and violently begins to boil again. The ice water chills the glass, which condenses the trapped steam inside back into liquid. This sudden lack of vapor creates a partial vacuum, dropping the internal pressure so low that the water's boiling point plunges well below 80 degrees. You likely have a device in your kitchen that does the exact opposite. A pressure cooker traps steam to intentionally drive the internal pressure up, forcing the boiling point higher so your food cooks at a much hotter temperature. Pressure and temperature act as competing masters. They constantly negotiate with each other to determine whether a substance gets to be a solid, a liquid, or a gas. The behavior observed in these tabletop experiments follows a rigid set of mathematical rules governing every substance in the universe. A phase diagram charts pressure against temperature, dividing states into solid, liquid, and vapor. The fusion curve marks where ice melts, the vaporization curve where water boils. The sublibation curve shows matter skipping the liquid phase entirely, turning from solid to gas. A phase change follows a sliding scale, determined by specific coordinates on this pressure-temperature map. Which brings up the ultimate theoretical question. What state do you get if you slide your coordinates to where all three boundary curves intersect? This intersection is the triple point. For water, it exists slightly above absolute 0 Celsius, under an extremely low vacuum pressure. Place a cup of water into a vacuum chamber and dial in those exact coordinates. The water will simultaneously freeze into jagged ice crystals and violently boil off into vapor, all at the exact same time. A phase change is a structural transformation. Heat provides the energy to shift the architecture, but pressure builds the walls that hold it all together.